We're going to be talking about the problem of statistical relational learning and a specific tool that we've developed at Maryland and now at Santa Cruz called Probabilistic Soft Logic, which is a framework for reasoning, modeling, and solving problems of this kind. So today we're going to talk about the problem of relational data and the field of statistical relational learning. Then we're going to dive into this framework that we've developed, Probabilistic Soft Logic, and talk about some of its foundations and also how inference and learning works a bit in it, and talk a little bit about applications. Then we'll take just a short break and dive into a hands-on demonstration, because we also have an open source implementation of our software, and we'll get started with that. So first, let's talk about relational data and statistical relational learning, or SRL. So much of classic machine learning has made progress with a particular view of data, and that is of independent points in a feature space, like in this picture. And you can do all kinds of tasks with this view. You can learn to classify points, predict back given labels. You can learn trends between continuous variables. And you can also, by regression, and you can also do clustering, sort of unsupervised grouping of these data points. And these algorithms in classic machine learning make two assumptions. And the first is independence, that if you know something about one of these points, it doesn't tell you about any of the other points. So for example, if you knew that one of the points in your data, one of your data points had a particular label, that wouldn't help you label any of the other data points in this, if you assume independence. And oftentimes you also assume identical distribution, that all of these points came from the same underlying distribution. And so this is sometimes called the IID assumption. And when you get a little bit farther in machine learning, you find that actually a lot of, and of course just when you think about it, a lot of the real world doesn't follow this IID assumption. And so people have looked at how can we try to relax this assumption, what else can we do? And so some people have looked at predicting small independent structures, like let's say parse trees. And so now you have things that are more complicated than just an individual point, an individual label, but you still have many small independent structures. But the real world, even this isn't how the real world works, right? In fact, there's a lot of real world data that I'll call relational data, that are made up of large interconnected networks of entities and relations among them. And so this has gone by a lot of different names. Structured data, network data, multi-relational data, heterogeneous networks are just some of the names. But what people are talking about when they talk about these kinds of data are, they're talking about many interdependent entities connected via relations. And this kind of data pops up all over in the real world. And so some obvious examples are social networks, where the entities are people, groups, interests, and the relationships are friendships, likes, affiliations, things like that. Of course, there's the web, and so you have pages and hyperlinks. And those pages have attributes, they have metadata, but they're all connected in one large network. And so you can't just carve out one piece of this network and say it's totally independent of everything else. You've got one large collection of relational data. Biological networks are another very common example. So for protein-protein interaction networks, drug-target interaction networks are examples of this. And then there's other types of data that are not as explicitly relational, but also fall under this category of being having entities, relationships, and many interdependent parts. So natural language is a great example of this. Of course, you can break down semantic webs into as relational data. You also text, just free text, has many implicit relationships among all the entities that are described in that text. And also video and images are often implicitly relational. For example, this data set comes from, or excuse me, this image comes from a activity recognition data set. And so what you're trying to do is identify what all of these people are doing in these pictures. And of course, what someone's doing in a scene is often related to, it's not independent from what other people are doing in that scene. And what people are doing in one frame is not independent of what people are doing in another frame. And so even though this isn't explicitly relational, like say the web is, this still falls under the category of relational data. And so some smart people got together and they realized that, okay, we need a field that models, that tries to build models of this more complex data. And so this was named the field of statistical relational learning. And so that's what we're going to be talking about today. And what statistical relational models do are model relational dependencies. So I've been talking about the dependencies among unknowns in these data sets. And another way of saying that is that some joint configurations of the unknowns are more probable than others. Okay, so imagine that I've got 3 people. And one configuration is that there's 2 friendship links here, that this person is friends with this person and this person is also friends with this person, and yet these 2 are not friends. That's one possible configuration of the unknown friends relationships. But we could say that there's a probabilistic dependency here, that's actually less probable than triadic closure, that it's actually more probable that all 3 are friends, that the friend of my friend is also my own friend. Another example is predicting political affiliations. And so you might say that it's more probable that people who are friends have the same political beliefs. And so one possible configuration is that these 2 people support one political party and this person supports another. And so you could imagine that there's a probabilistic relational dependency here, that it's less probable, this configuration is less probable, but it's more probable that they all have the same political affiliation. So these are simple toy examples of relational dependencies. And these kinds of dependencies are what we're going to use to model this interdependent, this connected data. And so statistical relational learning wants to model these relational dependencies and learn to predict the unknowns jointly. And so you don't even have to just predict links or labels in isolation, that all of these unknowns, who's friends with whom and which political parties they support, are all interdependent unknowns that we can build models of and predict them simultaneously. And so that's what SRL is going to do. And that's what SRL does. But how do we build these models? And so people have been working on this for a little while now. And in terms of probabilistic models, there's 2 big camps of work. And the first is generative models, probabilistic graphical models. If you're familiar with these are typically directed Bayes nets, directed graphical models. And these score different configurations in terms of conditional probability distributions. And examples of these include probabilistic relational models, blog, church, and relational topic models. These are different models for describing relational domains. And so some properties of generative models, that you get this nice generative story, that they're very interpretable. You can say that, okay, I sample, or this distribution generates this, and then condition this unknown, and then condition on that, I have another conditional distribution that generates something else, and so on and so on. And you get relatively easy learning, that oftentimes, because of this particular form of these models, oftentimes learning comes down to counting or measuring simple sample means, expectations, things like that. But you have to carefully construct these. So you have to make sure that your dependency structure is an acyclic graph. So you have to very carefully construct your models. And generative models model both the observations and the unknowns. And so before we were talking about, okay, with these 3 people, the unknowns are just who's friends with whom and who they vote for. But in a generative model, you'd also put a distribution over the existence of the people in the first place. And so you're modeling both the observations and the unknowns. And so an alternative to this is discriminative models, where you score different configurations only over the unknown components. And this often takes the form of what's called a discriminant function, which is just usually takes the form of a linear combination of potential functions. And so you have these weights, these parameters that control the relative influence of these feature functions that score different parts of your configuration. And oftentimes this gets a probabilistic interpretation. You can put this into a model in which the probability is I guess, log proportional to the value of the discriminant function, and then with a normalization constant to ensure that it's a probability distribution.
We'll
yes?
see like tons of things that have this general form. So this is like a highly general form that you'll see over and over again, even though every time it's written, it might be written like slightly differently, and so it takes a little while to squint at to recognize it.
Yes, exactly.
But if you think of things like CRFs, and, in that category, they all fit with this. And yeah, you were about to list other things.
Great, thanks. Yeah, and so some of the most common ones are Markov random fields, that can be trained as max margin Markov nets, structural SVMs, and Markov logic networks, which use a logical templating language to define these feature functions. And we'll come back to that because that's a very powerful ability, and we'll use that later in PSL. And so some of the properties of discriminative models is that they're easy to define. You don't have to worry about these acyclicity constraints, and so you can write down as many potential functions, many of those phi scoring functions as you can think of. Very easy to define. And then because you write down whatever you want, you have almost one-size-fits-all algorithms. Oftentimes, sampling and inference algorithms can be written down that apply to very large classes of these models. But there's an asterisk, and that is that sometimes these general-purpose models don't scale very well to all the possible things that you could write down. These models are so expressive that sometimes you can write down things that end up not being very tractable. So this is a problem we're going to be thinking about. And I'm sure it's something that you're going to revisit in this class can we do anything with this model? Is it tractable? And so that brings us to a particular SRL framework that we've developed, and it's called Probabilistic Soft Logic. And PSL is a declarative language based on logic to express SRL problems. And so what we're going to do is we're going to describe our domain, we're going to describe our problems in a logical language. And then we'll see how we can use that model that's easy to define to as a template for models that can solve problems for us. So let's talk about the components of PSL. And the first component of PSL is predicates, and these are relations or properties. So all the relations, the link types in your domain are different predicates. So for example, friendship is a predicate. And so when we want to use that in PSL, we'll have a predicate friends that takes some number of arguments. And here it's a binary relationship. Two people are friends. And then we have atoms, which are the random variables, the unknowns or the observed things. And an atom is a predicate combined with arguments. And so sometimes we'll be more specific and say that if you don't have variables but you have specific constants here, that's a ground atom. And a ground atom has a particular value. It's true to some degree or false to some degree. So for example, friends is the predicate, but whether Steve and Jay are friends is an atom. That's a particular thing that you're reasoning about. And in PSL, what separates it from many other SRL frameworks is these are continuous random variables. And we'll come back to why that is. But for now, just keep in mind that these are not just true or false, but they're true or false to some degree. So this is going to take what we call a truth value from 0 to 1 inclusive. So you could be friends to degree 0.9, let's say, and so that would represent a stronger friendship link than being friends to, say, 0.5. And then we're going to write down rules to capture the relational dependencies that we've talked about. And so, for example, before we talk about triadic closure, friend of a friend is also a friend. So we can write that in a very simple rule, like the one right here. And so it says that if A and B are friends and B or C and friends, then that implies that A and C are also friends. And note that there's a weight here, because oftentimes, that's where the statistical part of SRL comes in, that these things are not always true or always false. They don't always hold. And so some are more likely to hold than others. And we use weights to capture how strong they are. And these weights are just relative to each other. So it's not that 3.0 has an intrinsic meaning. It just means that it's more important, more likely to hold than a rule of a lower weight. And finally, we're going to have sets. And sets are aggregates over atoms. So for example, you can reason about the average value of Steve's friendship links. Does he tend to be strong friends with people, or does he tend to not be very strong friends with people? That's an aggregate that you can reason about, and we'll see where that comes in handy. And so a PSL program is the set of rules written down, made up of these relationships, applied to data. And we'll go through how that works. But what we'll do is these rule sets capture general notions, general relational dependencies about our domain that will then apply to data to solve specific problems.
Think about that going back to Tuesday's class, where we're talking about like all those categories of relational features and so on. A lot of this is to try and capture as many of those as possible.
Great. Yes.
All right, so related to that, a couple of questions. The first question is, so this is based on first-order logic, right?
Yes, but it's not a full first-order logic syntax, so there are some restrictions.
Okay, good. So
Yes.
Because one of the things that I would like to say is for any small a, say, capital A,
Yes.
for any A,
Mm-hmm.
you can write that through the
Yep. Yes.
And it probably gets to where you would like to express something like for any A, you loses.
Yes, yeah. So you're talking about universal versus existential quantification. And so by default, all of these rules are universally quantified, that they're going to be grounded out for all possible substitutions for A, B, and C, for example, in this rule here. Now, existential quantifiers are something that we've done some research on, and also other people have looked at. But that gets tricky, right, because when we dive into the details, what you have is essentially a probabilistic dependency on all the possible things in your universe. And so that's something that's still kind of an open question. We've done some work on, okay, how can we do that smartly? But that's a great question. So just keep in mind that right now we're talking about universal quantification. And did you have another question?
No,
That's great. Okay, great.
Yeah,
Thanks.
and actually it is a very active area of research in the group because in a smart way, because either of doing latent variable stuff, but then we also have some like mapping stuff that students can
Mm-hmm. Yes?
Can these weights be negative, or do you just write the, are you supposed to just write the?
No, they can't. So some frameworks support that, but what you could do is you could say, exactly, you could put a not in front of the head and basically get the same effect. And so, it's non-negative, so it's from 0, meaning that this rule has no effect. It's not actually a dependency, to effectively infinite, which means it's a constraint. It always has to hold. That's a great question. And then I just point out that so what separates PSL from some similar SRL frameworks is the continuous random variables and the aggregates. That's sort of the main unique features, and we'll talk about why those are useful. So let's talk about how we might use this idea of writing down relational rules to model real problems. And so one problem that you might have is entity resolution. In data, do two references refer to the same underlying entity? And this is a problem that you're going to talk about a lot, I'm sure, in this class, and it goes by many names, but entity resolution is one of them. And so in this domain, you have people references. You have names in databases. For example, if somebody filled out a form, maybe they used their full name, maybe they used just their first initial, and so there are these references. And then you might have a social network, actually. You might actually know, for example, in this form might be for a social network, and so maybe you also have relationships, friendship relationships among the references in your data. And your goal is to identify references that denote the same underlying person. And so some of the relational dependencies that you can use, we can express as rules. And so the first thing you might say is that if two people have similar names, they're probably the same. Make sense? And so this is the kind of rule that you'd write in PSL. You'd say that if somebody has a name and somebody else has a name, and those names are similar, then they're the same person. And it has some weight, 2.0. You know, not too high, not too low. It's a pretty good rule. And so what we've done is we've taken this intuitive relational dependency that we have in our heads and put it into a form that will actually allow us to computationally reason about it. Okay, so that's just one rule.
And then, as Steve said, we'll be talking about this in more depth throughout the kinds of things that similarity function typically comes for string as simple as edit, but it also could be typos or in other kinds of things. You can make this as fancy as you want. And then on top of it, a lot of what we've done in PSL has been, how you combine together multiple similarities. So you could have a bunch of different string similarities or a bunch of other similarities coming from experimental data or something like that. How do you use PSL basically as a fusion tool to fuse all this information and propagate the information?
Great, thanks. Yeah, that's a really important point that I'm glossing over what that similarity function is. But that's a feature that you can include in your model. And so now, the next one we say, if two people have similar friends, then they're probably the same. And so this is where the aggregates come in. And so rather than reasoning about individual friendship links, you can say that, okay, if two people have similar social networks, then they're probably the same person. And again, we can write down this rule very simply. And so later on in the hands-on demo, we'll talk about how we define this aggregate similar friends. But once you have that notion, it's very easy to say similar friends implies that you're the same person. And finally, we can have transitivity of identity of equality. So if A is the same person as B and B is the same person as C, then A is the same person as C. And this is also really easy to write down. And see, we've given this a very high weight because this is something we expect to hold quite often in practice. And so already we've taken this problem of entity resolution and put some of our relational dependencies into a form that PSL can use. And now another problem is link prediction, predicting relationships in your data. And so if we have an email network where there are people and messages that they've sent to each other, this could come from a social network. There's a famous Enron data set that is of this type, but any kind of communication network. We have entities that are people and emails. Attributes of those entities include words in the emails, and then there's relationships, communication, work relationships in the sense of who supervises whom, who's a colleague with whom. These are all things that we might want to predict. And so our goal is to identify those work relationships, supervisor, subordinate, things like that. And so again, we have rules that express the relational dependencies that we want. So the first thing we can do is we can try to figure out what kind of email a particular message is in this communication network. And we can use features, we can use attributes of those emails. So if for example, if the email content suggests that it's of a particular type, then it is of that type. And so what we do is we write down a rule that says that if a particular message contains the word due, as in it's due by a particular date, then it's a deadline email. That's a rule that we can write down. And notice here now we don't have variables for all the arguments. We have a particular parameter that characterizes how much a particular word is indicative of a particular type of email. So now this is slightly different, but this is another type of dependency that we can put into our model. And now we can reason about these links that if you send a deadline email to someone, then you're likely to be their supervisor, right? So if A sends an email to B that has an email E, and that email E has the type deadline, then A is the supervisor of B. That's another rule we can write down. And finally, we can reason about these unknown links simultaneously. That if, again, if somebody is the supervisor of two people, then those two people are colleagues. And now, a third type of problem is collective classification. So we talked about classification very briefly in the beginning, where you want to label entities in your domain. And so a really important problem, a particular problem, an interesting problem, I think, is predicting opinions, such as political opinions of people. And so we already have some idea of how to do this from classical machine learning. And so things like logistic regression, naive Bayes, these types of classifiers, we already know what some of the features that we want to include in our model. And so one thing we might do is, if we know that somebody donated to a particular party, then they probably support that party. Donations above a certain amount are public information, so that's a feature we might have. we'll give that a high weight because if you're donating to the Republicans, you'll probably support them. And of course, we have other types of features that if you mention the Democratic president in say, a tweet or status, that you are more likely to support the Democrats, let's say. That's a feature we might put in. But now, this is all looking at an individual classification decision. But what we already said is that these are not actually independent, that we have relational information as well. We have a social network, potentially, of different people. And since these, we expect opinions to be correlated amongst people in a social network, what we want to do is we want to predict all of these things simultaneously. And so what we're going to do is we're actually going to label this entire network simultaneously. And now we can put in additional features, like if you're friends with someone and you vote a certain way, then that person is also more likely to vote a certain way. And we'll give that, a weight of 1.0. And we can define these features for different relationship types because we expect them to propagate opinions more strongly. So maybe friends, has a weight of 1.0, but if you vote a certain way, your spouse might be particularly likely to vote that way. That's one model that you could construct and see if it fits the data. And so we give that a weight of 5.0. So now we've talked about three classic problems, three core problems in statistical relational learning. And we've talked a little bit about how we'd encode those problems in probabilistic soft logic. But now what we have to do is dive down into the foundations, the logical and probabilistic foundations of PSL, and think about how do those dependencies get turned into real models. So we'll start by looking at those rules that we've defined. And remember, we wrote them down and they have variables in them. So they're lifted rules. They're not ground yet. But the first thing we do is we apply these rules to data, and we instantiate a particular ground rule for every substitution in the input. Right, so every substitution for the variables based on your data results in a ground rule. And remember, each of these atoms has a truth value that's real valued, and it's in 0 and 1. So now we have to say, okay, what do those combination functions do? Those ands and ors in our rules. How do those actually get interpreted? We know how they get interpreted in Boolean logic, but how do they get interpreted in this continuous soft logic? Well, the first thing to keep in mind is that they're going to behave very intuitively. They're going to behave in an intuitive way just like Boolean logic, that rules are satisfied or happy in a certain sense under certain conditions. And so if the atoms in the body have low values, the rule's always happy. This is just like in Boolean logic. And so, for example, if we have this rule about transitivity of friendship, and the atoms in the body have low values, then the rule is always happy. If the atom in the head is high, rule's happy. And if the atom in the head is low, rule's still happy. And again, just like Boolean logic, even if one of the atoms in the body is high, rule's still happy because the entire body has to have high truth values. Okay?
And so just kind of expanding out like in Boolean logic, if the premise is false, then you don't care about what happens with it.
Yes, absolutely.
Just in case, to hear it said another way.
Thank you, yeah. And so now, but of course, with the implication, if the body has high truth values, then the rule is only going to be happy if the head also has a high truth value. Okay, so now if the body has high truth values, and the head also does as well, then the rule is happy. But if the if the body has high truth values and the head has a low truth value, the rule is unhappy. Okay, so does everybody see that this is behaving intuitively just like Boolean logic? But now,
but
yes.
all of it. And sorry for.
No, please.
Just trying to make it more interactive, so you guys can jump in with questions too.
Yeah, please do.
But the whole thing is this.
I'm not getting the second one.
This one right here?
Yeah.
Yeah. So if I write a rule that says if then.
No, I mean the graphic wise, I think both are the same one, but then can you just.
Yeah. So what I'm saying is, imagine if the atoms in the body here have high truth values. So Jay and Steve are friends, and Steve and Ben are friends.
Yeah.
and Jay and Ben are friends. This rule is satisfied
Yeah.
because it holds. If this, then that. Okay?
Yes.
But now imagine if Jay and Ben weren't friends. Right? So now we consider a different assignment of truth values. Well, now the rule's unhappy because you said if this, then that, but then that didn't happen.
Yeah.
Okay? Does anybody else have any? That's a great question. Any other questions? Great. So, but this is all very hand-wavy, right? I'm still just trying to convey an intuition here. We need to actually specify, okay, mathematically, what do these functions actually do? And so we're going to use what's called the Lucas-Yavich T-norm. And that, what that means is that these are going to be piecewise linear functions that combine these truth values as defined here. And so what you could do is you could see that these are actually exactly the same as the Boolean operators for extreme truth values. If you only plugged in 0 and 1 for truth values, only integer values, you'd get they behave exactly like Boolean logic. Okay, and so this is a relaxation, an interpolation of all the continuous truth values between 0 and 1. And now we'll see how these actually work, okay? Because we talked about a rule is happy. Well, what does that actually mean? Well, we say a rule is satisfied under a particular condition if the truth value of the head is at least as big as the truth value of the body, okay? So imagine I have a rule like we had before, and I assign 0.7 and 0.8 to the atoms in the head. So let's say Steve and Jay are friends to 0.7, Jay and Ben are, or Steve and Ben are friends to 0.8, then under what conditions is this rule satisfied? Okay. So now let me actually jump back here. Does anybody think they could figure this out? Does anybody tell me? So what's the truth value of the body? Okay. Yeah. So just remember it's 0.7 and 0.8. So now using this, what is it? Yes, it's 0.5. So the truth value of the body.
I have a question.
Oh yes.
Actually.
Yes.
I don't remember what the word is, like commutative or distributive or the one where.
Yes, so they follow De Morgan's laws. They work just like Boolean operators. Yeah. Yep. Yep. And you're right. Yes. So the truth value of the body for this particular assignment is 0.5, and so this rule will be satisfied for any setting 0.5 or greater to the head. And what we say is it'll be perfectly happy under that condition. So now we've really nailed down a little bit what it means for this rule to be satisfied. Okay? But let's say we don't meet this condition. Let's say it's not 0.5 or greater, and it's not perfectly happy. Well, then what happens? Then we can talk about a distance to satisfaction. Okay? And so this is just a fancy way of writing it down. You're saying, okay, what's, how far away are you from satisfying that condition? It's either 0 or the difference between the body and the head if that number is positive. Okay, so it's just a question of how far away is that. So again, the truth value of the body is 0.5. Same setting we had before, 0.7 and 0.8. And now let's say we assign a truth value of 0.7 to the head. What's the distance to satisfaction? No, it's 0. That's right, because the head is greater than the body. Okay. But now, same thing. What if I assigned a truth value 0.2 to the head? Now what's the distance to satisfaction? Yep, 0.3. You guys got it. So now we can say what it means for a rule to be perfectly satisfied, and we can also talk about how far away it is from being satisfied, and that's called the distance to satisfaction. Okay? And finally, remember that we had weighted rules. We had rules assigned to the weights, and this is where that's going to come into play. Okay, because we can now talk about a weighted distance to satisfaction. If a rule has a particular distance to satisfaction, then we can multiply it by its weight, and now we have a weighted distance to satisfaction. Okay, that was a lot of information. So let's take a step back and review what we've talked about so far. If you have a data set, some set of relational data, and a PSL program, we can construct a set of ground rules. You can do all the substitutions for all the variables in your rules and come up with a set of ground rules. And now some of those atoms have fixed truth values. They're observed. We know them. Let's say we've observed that these are the people in our data set, or we know that this person sent that person an email. Those have fixed truth values. But some of them have unknown truth values. We don't know if this person is a supervisor of another person. Okay? And those are the unknowns, the things we don't know. And now what we can talk about is we can talk about assignments of truth values to those unknown atoms. And for every possible assignment to the unknowns, we get a set of weighted distances from satisfaction. So I give you all your ground rules, and I say, okay, I just made up these numbers. Here's some assignment to all the unknowns in this model. Then you could say, well, here's the set of weighted distances to satisfaction. And there'd be one distance for each ground rule. Great. So now we get to the question, which assignment should we give to those unknowns? How do we decide which is best? And that brings us to probability theory. Okay? And so the short answer is we're going to put this in a probabilistic model. And we're going to put a probability distribution over all those possible assignments. And the probability will be determined by those weighted distances to satisfaction. Okay? And remember, you've already seen this when we talked about discriminative models. You've seen this form of model before. Okay? And so for PSL, we're going to define a probability density over interpretations, over assignments of truth values to the unknown atoms. And remember, this is a density because it's defined over continuous variables. The truth values are continuous. And so what we do is we have one grounding, one feature, for every ground rule in our model. And the value of that feature is the rule's distance to satisfaction. And the parameter that weights that distance to satisfaction is the rule weight. And then what we'll do here is we'll have a distance exponent. We'll either leave it as it is or we'll square it. And this just determines whether how the model is going to trade off between competing assignments. Does it trade off more smoothly or more of a winner-take-all system? And we won't have time to get too much into that, but of course, if you want to learn more about that, come to office hours. That'd be great. Okay, so now this probability density is just E to the negative sum of all those weighted distances to satisfaction. Okay, so the more distance to the farther you are from satisfying rules, the more probability you lose. And the higher the rule weight, the faster you lose probability. So what that means is that the higher the weight of the rule, the more important it is to satisfy that rule. And finally, of course, to make this a valid probability density, we'll have this normalization constant right here. Okay, and we've been doing some research on this type of ground model that's a generalization of the things you can get from the rules that you write down. We call these Hinge-loss Markov random fields. And so this is just a fancy name for the underlying probability distribution, and it's related to discrete Markov random fields if you're familiar with that, except the potential functions are hinge losses. And so PSL models always ground out to hinge-loss MRFs. This is just a particular type of graphical model. And in a hinge-loss MRF, you have continuous variables in the 0-1 interval. Those are your truth values. And your potentials are hinge-loss functions. So those distances to satisfaction, those functions are hinge losses. And it's going to be subject to arbitrary linear constraints. So we'll see that that will let us include hard constraints, hard rules in our model. And this is where we get to the first advantage of using continuous variables. This makes a log concave density, and we'll see that that's going to make inference really tractable. Okay, there's going to be one unique assignment or one flat plateau of assignments that are all equal probable that are better than any other according to the model. Okay, and so that's the underlying distribution here. Okay, so now you had a lot of information. I just threw even more at you, and so now what we're going to do is work through a program all the way down to the underlying probabilistic model. Are there any questions, anything before we dive into that? Yes?
I can provide question.
So this is basically a conditional random field.
Yes, yeah.
You have there the conditional, but it's not clear who y and x are. What are conditioning from? Are you conditioning when zero variables?
Yes, yes, and so Markov random fields are closed under conditioning, and so you can think that there are some observations that you get that are, and so this is just the conditional form of writing that down. And so if you've observed some truth values, those are just fixed variables in your model, and so
you're modeling the density just for those.
For the unobserved values, yes, that's exactly right. And so that's a good point. I've written this down in the conditional form, but it's exactly the same. And so I'm just conditioning on the truth values that we have observed. Great question. Anything else? Great.
Is there any influence of this?
Okay, so let's go through a toy example. So imagine that I have, or I want to build a social network, okay? And so I have some people. I've got 4 people, and I know that they have some interests, okay? So now I have entities, and I have attributes on those entities. I have people, and I have the things that they like. So now what are, but I want to build this social network, okay? And so the relationship is friendship, but I don't have any observed friendship links. And so can anybody tell me, let's see, how many unknowns are there in this domain? Okay, so anybody can be friends with anybody. What's that? 4 choose 2, which is 6, yes. That's right. Okay, so these are the unknown atoms in our domain, all of these possible friendship links, okay? And so that's what we're going to write a model to predict, okay? And so let's say I give you this rule set now. And what this rule set says is that people who have similar interests are friends, and friendship is transitive, right? So if this is A is friends with B is friends with C, A is friends with C. That's there again. And then finally, I have a special case rule. Okay, the people who have particularly incompatible interests are not friends. Okay, we're going to write down this rule too. So monster truck rallies, maybe you're like this really high-strung person. I don't know, you're an adrenaline junkie. Maybe you're not likely to be friends with someone who likes nature walks. Okay, so this is our model. And finally, our 4th rule is can be thought of almost like a prior. That we're just going to say that if we don't have any evidence saying that you guys are friends, then it's more probable that you're not. Okay, and so that's just going to be for well-formed models. And so to construct our ground probability distribution, the first thing we do is we ground out all those rules. We do all those substitutions. Okay, and so we take a rule and we come up with all of the possible substitutions based on our domain, right? So for this rule that says that people with similar interests are friends, we do all the possible substitutions, and so we substitute all the names, all the interests, and ground these all out, okay? And then finally, and then next we have this special case rule. And here, we're only going to do the grounding for people that actually have these special case interests. Now, in one view of the model, all the groundings still exist, they're just false, right? For example, Claudia could be interested in monster trucks, but since we already know that's false, that's an observed, we're not going to ground that out. Okay, so this is the only special case rule, the only instance of the special case rule in which the body is true. Okay, so we're going to ground that out. And finally, we could also do the substitutions for the transitivity rule. And of course, we also substitute for the prior. So after we've done all of those groundings, we have a set of ground rules. Everyone with me so far? Great. And now we're going to convert those ground rules to Hinge-loss functions. We're going to convert them to the functions that tell us our distances to satisfaction. And so let's do that for one example. Take a ground rule. It says that if Allie and Brad are friends and Brad and Dave are friends, then Allie and Dave are also friends. Okay? And we're going to map those to atoms to random variables. So we don't know any of these friendship values. They're all unknowns. Okay? And so we've got 3 random variables, each of which represents the truth value of one of these atoms. And we're going to apply those t-norms, the Lucas-Average t-norms, and we get this function here. Okay? And then what we do is we subtract from 1 to find the distance to satisfaction. This measured the satisfaction, so we subtract from 1 to get the distance to satisfaction, and we get this hinge loss. It's the max of a linear function and 0. And now, what we do is we do that for all of our ground rules, weight them by the weight of the rule that generated them, and embed them in a Hinge-loss Markov random field. So that max function is this function right here. It's the max of a linear function and 0. And we've got a sum over all of them for all the groundings. And so now we've gone from a relational domain, a set of relational data, with a PSL model all the way down to a ground graphical model that we can actually do reasoning in. And so the first thing we want to do is we want to do inference. We want to make predictions. And the way we're going to do that is by finding what's called a most probable explanation. And that's just a big mouthful for saying, what's the best y? What's the most probable y? So if people have background in graphical models, it's okay if you don't, but if you do, you know that there are different questions we can ask our probabilistic models. We can ask for marginal distributions over particular variables, or we can ask for the map assignment, the most probable assignment to some subset of the variables. And so MPE is a particular type of query that says, give me the most probable setting to all the variables. Okay? That's what we're going to be asking for. And if we go back to the form of the distribution, we find that the thing that maximizes the probability distribution minimizes that discriminant function. Okay? So to answer the question, who's friends with whom, or whatever question you want to answer with your PSL model, you've got to minimize this discriminant function. Okay? And what that works out to is minimizing a weighted sum of hinge losses subject to linear constraints. Now you might be saying, well, why the most probable explanation? Why are we looking for that? And of course, like I said, it's the best scoring assignment to the unknown variables. But you might also think, wait a minute, it's continuous valued. Okay, I can understand that friendship and similarity, like sometimes modeling things in a continuous domain is an advantage because many things are not discrete. So that's the second advantage of working in a continuous domain. But you might say, well, my problem isn't continuous. What am I going to do with these continuous values? And how should we interpret them when we run this query? Okay, and there's some simple things that you can do that work great in practice. You can just round them, which is simple enough. Or sometimes what's more common is to treat them as a ranking. Okay, because oftentimes you're predicting rare things. For example, friendship links are rare. Think about how many people are how many pairs of people are friends versus how many pairs of people are not friends. And so what you're going to do is you're going to say you're going to want to treat this as a ranking. Just treat these values as confidences from the things you're most sure exist to the things you're least sure exist. Okay, so you've got a couple ways of interpreting these continuous variables. And when we get to real-world applications, you'll see that that's what we do in practice.
And just in case
Yes.
anybody's not clear what rounding means, what we mean is
Oh, yes.
have it either be 1 or 0, whichever is closer to.
Yes, yeah, if you need that discrete value, yes. Thanks. So now, like I said, we want to minimize that discriminant function. And because we carefully constructed this, that's going to be a convex optimization. So if you're familiar at all with optimization theory, you know that convex optimization is, well, I don't want to say the best, because that might rub some people the wrong way, but it's the easiest generally, and so it's going to be really nice to work with. Okay, so in PSL, MP inference is a convex optimization problem, and that's awesome. And you could use off-the-shelf toolkits. There are many things that will solve generic convex optimization problems for you, but even then, really, as you know, as you're learning, relational data can be huge. Think about how big the web is, how big real-world social networks are. And so even off-the-shelf toolkits, while they'll be more scalable than doing combinatorial optimization in a discrete model, it might not be the best tool for the job. So the best general methods have supercubic time complexity. So these are things like interior point methods, if you're familiar with those. But what we've developed is a specialized optimization framework that scales even better. And this is, I'll just sort of gloss over these details because we're really down into the details here, but this is what's called the alternating direction method of multipliers, which is a really long term for decomposing the problem into independent subproblems and then coordinating the solutions until they all, by voting, until they all agree on the solution. And so what we'll do is we'll decompose this problem into all the independent distances to satisfaction. All those individual phi functions, those potential functions, we will optimize them independently and then have them vote on the solution until they all agree. So what each one says is each one optimizes for itself, each ground rule, and says, okay, I think the values of these variables should be this, this, and this. And they all vote. And then you average those votes, and then the subproblems are solved again, and they say, well, this is the solution, this is the thing that minimizes the distance to satisfaction that's also close to the emerging consensus, that's also close to the average of the votes. And then they vote again. And you keep going. And the nice thing, because this is a convex optimization, is that it's guaranteed to converge. And so you'll get that MPE state. auxiliary variables, if you're familiar with Lagrangian relaxation, ensure that the consensus is reached among these subproblems. And what you see is that this scales much, our Java implementation of ADMM is going to scale much better on these types of problems than very expensive commercial interior point methods, general purpose solvers. And what you see actually is that in practice, we see a sort of a linear time scaling with the size of the inference problem. And we've taken this out to, by we I mean Jay has taken this out to, Jay and some of his collaborators have taken this out to tens of millions of variables, or tens of millions of potential functions of ground rules, and you still see this linear time scaling. So this is highly scalable, and that's going to be really important as you apply this, as you work on big SRL problems. And something that we're starting to work on, some other people in this group are working on, is GraphLab implementation. So if you're interested in vertex programming, real types of scalability, that's something we're starting to work on. And so if you want to talk some more about that, definitely come to office hours, because that's something we're excited about. And then I'll just touch very briefly on learning. So up until this point, the rules for those weights have been hard-coded. I've been throwing around these intuitions. Well, you expect this rule to hold more often than this rule, so we'll give it a higher weight. But of course, this is a machine learning class, and so let's get to the real learning stuff. You want to, oftentimes you want to learn these weights from data. You want the data to tell you what the weights of the rules should be. And so I won't have time to get into the details here, but I'll just say that we can learn the weights from training data. There's no need to hand code the rule weights, and we have various methods for doing this. We have approximate maximum likelihood, where you want to maximize the likelihood of your data. And there's also other methods like maximum pseudo likelihood, which is maximizes the likelihood according to a decomposed conditional distribution, if you're familiar with that, and also large margin estimation. So that's a generalization of support vector machines to these from binary classification to these graphical models. And so we have various methods that are implemented in our open source software that we've developed to learn the weights of these rules. And now I'll just very briefly touch on a couple of real-world experiments. So one thing you might want to do is collective classification. And so one instance of collective classification is given a networked collection of documents, such as a citation network, so you've got a bunch of papers and they have links among each other because they all cite each other, or you have Wikipedia pages that have categories that all link to each other. You might observe some of the labels. Maybe somebody has already gone through and labeled some of your documents for you. Well, how can you use that to predict the remaining labels using the link structure? Because you assume that documents of a particular category are more likely to link to each other than documents in another category. And so what we find is, right off the bat, when compared with discrete Markov random fields defined by Markov logic, which are another SRL framework, we have improved accuracy compared to the approximate sampling methods that are required for the discrete models. And another problem is, and I'm just going through these very quickly, is social trust prediction. If I have a network and I want a social network and I want to predict who trusts each other, maybe I observe some trust links and I want to say, who else are you likely to trust? And I can encode different social science theories, such as transitivity, anti-transitivity, so the enemy of my enemy is my friend. These kinds of intuitive things I can encode using PSL rules. And again, we find that we get good performance, good accuracy, especially compared to other competing methods. But where PSL really shines is how scalable it is. So what I showed just now is that, okay, we're doing slightly better than the comparable discrete models, but when you look at how long it took, how much time it took to get those results, that's where you see a very stark contrast. So Cites here in Cora are citation networks, and eOpinions is a social network where we predict the trust. And this is the amount of time in seconds required to find an MP state. So we're talking less than a second to do inference versus a couple of minutes to do enough sampling in the discrete MRF to actually get almost as good results. And these are not even gigantic graphical models, right? I'm not trying to tell you that they are, but already you see that there's a stark contrast in running time, and that running time only, that difference in running time only gets more dramatic as you move to bigger problems. Okay, you guys have been great hanging in there. We've gone through a lot of stuff, and so I want to take some questions if anybody has any, but also let's take just a 5-minute break.